Hi everyone, welcome back. Today what we'll do is look at HFSS and see how we can plot various quantities. So in the last video we looked at designing a patch antenna and then extracting the fields. But today we can take it a little bit further and look at how to plot all the different quantities that we care about. Because in the last lecture video of this course, we defined different antenna parameters and antenna concepts. So we would like to plot all of them and see what they look like. Okay, so we'll start with this simple patch that we designed the last time. And I deleted some of the plots that we did last time, but we'll go over it again pretty quickly. All right, so the first thing that we usually care about is the S11. So this gives you the impedance matching at the input. And we saw this last time at 10 gigahertz, it's well matched. So most of the power gets reflected at other frequencies, but at 10 gigahertz, it goes into the antenna. And which means it's pretty much getting radiated because this antenna is quite lossless. So the impedance bandwidth is given as the bandwidth at which, over which the S11 is less than minus 10 dB. Okay, so what you can do is you can place a marker, rather you can place a Y marker and then set this to minus 10 dB. And then this is the bandwidth, right? So 10.087 minus 9.941. So that's around 45, 46 megahertz or so. And so it's fairly narrow band. And that's pretty typical, 50 megahertz. So yeah, okay, that's about S11 and the impedance bandwidth. The next quantity that we typically care about is the gain or the peak gain. So we can also plot that. Peak gain in dB, make it sweep, and then send your report. So the gain's around, you can say, at maximum. So at 10 gigahertz, the gain is maximum. It's around 7.327 dB, right? And if you want this plot to be more smooth, you need to change the sweep to discrete. Okay, so that it actually solves it solves all frequency points that you mentioned here. Interpolating only solves a few and then interpolates such that the S parameters are converged. All right, so that's the peak gain. Then another one is peak realized gain. So we didn't really talk about this in the lecture video, but it's pretty straightforward. So, gain is efficiency times directivity. So peak gain uses the radiation efficiency, whereas gain uses radiation efficiency, whereas realized gain uses total or antenna efficiency. So let's plot this. Sweep over frequency, you can make a new report. Right? And you see that actually the gain is not that broad in frequency, right? And this would actually be even sharper if I solved at all frequencies. So let me actually quickly do that and show you what that looks like. Okay, so what I did is I changed this to 51 points and made it discrete so that it actually solves exactly at these 51 frequency points. And it finished its meshing and finished the original solution, and now it's doing the frequency sweep. So you can see the original solution was solved at 10 gigahertz, and now it's starting from the highest frequency and slowly going down and slowly solving all of these frequency points. So you'll get a more continuous graph. And you can see that that's kind of happening now. Okay, of course, you can make this even more smooth by increasing the number of points, but for now, this is probably good enough. Okay, so there is another bandwidth that we report apart from impedance bandwidth, and that is called the gain bandwidth. So that would be the 3 dB gain bandwidth, so which means that you would place a marker at maximum. This is almost done. All right. Clear all these errors. Not that important. Add maximum. So the maximum is 7.21, let's say. And I want to add a Y marker at 4.21. Okay, and that's my bandwidth, right? So this is the bandwidth of the realized gain. You should always report the realized gain bandwidth, not the regular gain bandwidth, because I mean that can be very large, right? Because it doesn't include the matching. So typically we report realized gain bandwidth, impedance bandwidth, and also axial ratio bandwidth. I'm going to update this, which we'll look at later. Okay, so that's about the realized gain. Of course, there's also directivity, which you can plot. Peak directivity, right? So let's also do that. New report. Okay, so that's the peak directivity. You can see it's very close to the peak gain, right? So for example, what we can do is I can say copy data, go into peak gain, and then say paste. I guess it doesn't want to paste in the same plot. Anyway, that's fine. Okay, so we're done with gain, realized gain, directivity, and this is all the peak values, which means it picks the maximum along some direction and plots that. Okay, so typically when you buy an antenna off the shelf, it provides gain as a number. It's this peak gain value. Okay, and then of course we also want to plot radiation efficiency. So radiation efficiency, I'll say times 100 to get the percentage. And again, we want to sweep radiation efficiency times 100, new report. Okay, so it's close to 90%, right? But now if you look at total efficiency times 100, maybe I can add trace. It's way different, right? Because it's not really matched at other frequencies. So peak values are almost the same because the S11 is almost minus 20, minus 30 here. But over the rest of the band, the total efficiency is quite low. Okay. All right. The other things that we care about is the impedance. So we go to model solution report, rectangular plot, Z11. And I usually plot the real and imaginary parts of Z1. Okay, over the sweep, so hit new report. And that gives you the real and imaginary part. And you can see there is some kind of a resonance, right, at this frequency. So there is a real part, which is maybe close to 50 ohms or so, which you can put a marker and see how the marker went over there. The marker here is around 42 ohms, right? And then there's an imaginary part, which looks like a resonance plus some inductance, right? Because it's positive. It's not like a pure resonance. There are reasons behind that. We'll maybe look at it later. But that's how you plot the impedance. Okay. Another thing you can plot, which will be more relevant to us later when we do wave ports, is the port impedance. Okay, so I can also plot this, and this will be exactly 50 ohms because it's a lumped port, and we define what the port impedance is, right? 50 ohms, and we renormalize it also to 50 ohms. So if, for example, if I change this to 60, all of these quantities will change because the mismatch, you'll see a mismatch now, right? So that's how you can kind of test. If my source impedance changes, then you can renormalize to your source impedance or your port impedance and see that everything that involves impedance matching will change. Like the realized gain will be different. The efficiency will also change. Okay, and of course, you can see that this has changed, right? All right, so Z11 doesn't change with port impedance, but S11 changes. It's important to remember that. Okay, and we can kind of test that if you like. I can make this 10 ohms. Then it's a very bad mismatch, right? So let's see what happens. Right, so it has moved now. It's now no longer matched at 10 gigahertz. Okay, and that makes sense because if you look at Z11, it's falling. So around 10 ohms, maybe it's a better match at a slightly higher frequency, right? Whereas looking at S11, it's very hard to kind of tune that. So if you want to match an antenna, sometimes it makes sense to look at Z11 because it doesn't change with port impedance and see, okay, if I want to match at 10 ohms, then what do I pick? Sorry, if I want to match at 10.1 gigahertz, then what impedance should I pick? You can see that from here. Whereas it's not always obvious to see that from S11. Okay, so what's the difference between renormalized impedance and port impedance? So if you change this, then you need to rerun the simulation because it will calculate the fields again based on this impedance and the current that you use on the port or the power of the port. Whereas if you use this, it just changes post-processing value and you don't have to resimulate the whole thing. Okay. All right. This makes more sense. Sorry. This makes a lot. So now you see it's 10 and 0, right? Because of what we set here. Of course, you can also make this imaginary. You can also add an imaginary component to this plus j times 20. Maybe it should be I. Is it 1i? Yeah, 1i. So 1i corresponds to imaginary part. So now you can see the imaginary part is 20 and the real part is 10. Right? So that's how you can renormalize. So let's go back to 50. So now, of course, plotting this doesn't make sense because it's the same as the port impedance that you set here. But when we do wave port later in the class, we'll see that plotting this makes sense. This because that will determine the impedance of the wave port mode. Okay, and we'll see that later when we do wave ports versus lump ports. Okay, so these are many of the quantities that we like to plot as a function of frequency. Another thing is the axial ratio bandwidth. So for that, we need to go into the far field parameters, click axial ratio, click dB, change this to sweep, change this to frequency because we want to sweep it as a function of frequency. But then you have to go into this family and select the bore site value. Bore site is, in this case, theta equal to 0 and phi equal to, doesn't matter because theta is 0, phi is anything, can be anything, but I usually like to set it to 90 degrees. Okay, theta 0, phi 90, axial ratio dB, frequency, we can set new report, and that should plot the axial ratio. Okay, and usually an axial ratio above 20 dB is considered linearly polarized. So this is even more than that, right? 50 dB is huge. And here it's kind of going off to infinity, sort of. So yeah. So of course, patch is supposed to be linearly polarized, especially this kind of a very symmetric patch. So that's what we have. Okay, that's the axial ratio. And of course, axial ratio bandwidth is only relevant when you're plotting the bandwidth, the axial ratio for a circularly polarized antenna. So in a circularly polarized antenna, you'll see that axial ratio will be close to 1. And then the axial ratio bandwidth is the bandwidth over which the axial ratio is less than 2, right? Or less than 3 dB in dB scale. So here, of course, everything is linear. So it doesn't make sense to plot axial ratio bandwidth here. Okay. The other quantity is polarization ratio, which we did not define in the lecture, but we can take a look at it. So let's say rectangular plot, polarization ratio. So the polarization ratio is defined as, so let me actually show you what it is. Okay, so in the far field, E vector has two components, E theta, theta hat, and E phi, phi hat, right? So depending on what kind of an antenna you have and how you've oriented it, if it's theta polarized, which means in the far field, E is along E theta, or it's supposed to be along E theta, then E copole is the E theta component and E cross pole is the phi component, which is cross to the co, right? That's how it's defined. If you oriented your antenna such that the copole, the desired polarization is around E phi, you want that to be E phi, then E co is defined as E phi and E cross is defined as E theta. Okay, and then the polarization ratio is given by the ratio of E co to E cross. Okay, so in dB it would be 20 log of that. And in HFSS, we'll see now that you can define different types of polarization ratios. So you can plot the theta polarization ratio, which is E theta over E phi, or the phi polarization ratio, which is E phi over E theta. Now you can also you can also say co and cross in terms of LHCP and RHCP, which is the left-handed circularly polarized and right-handed circularly polarized waves. We haven't seen this yet. We'll see this later in the class. But I just want to mention that polarization ratio for circularly polarized antennas is also defined. It's not really defined for elliptically polarized antennas, but for linear and circularly polarized antennas, you can define it. Okay, because there's a desired polarization and an undesired polarization, right? So it's different than axial ratio because axial ratio is defined for any kind of polarization. And it's important to know both of them, right? For example, you can have infinite axial ratio because you have polarization along E theta. Sorry, because it's linearly polarized. But let's say it's not polarized along E theta or E phi and somewhere in between, right? Then the polarization ratio would be low. So it's important to also mention polarization ratio because that in some sense defines how pure is your polarization compared to what you want. Okay. All right, so going back, so now we actually see that there's LHCP, RHCP, we won't bother with these right now. And there is theta and phi. So first we need to determine how our antenna is oriented and what the polarization direction is like. Right, so we have our patch antenna, and we'll see later in the class that if patch is excited here, then the currents actually flow along y hat. So along this direction, we'll actually plot today the currents as well. And we'll see that the currents flow in this direction along y hat. If the current is along y hat, then in the far field, the electric field is also along y hat, right? Because far field electric field is J cross R hat cross R hat. So we essentially get back J, one component of J at least, right? The component that's perpendicular to R hat. So the electric field is along Y, which means that in the far field, if I look at the electric field, it's Y hat direction, right? So Y hat direction, if the electric field is in Y hat direction and the K hat or the K vector is along Z hat direction or R hat is along Z hat, right? Along the Z axis, then the E plane would be the YZ plane, right? It's always the plane that contains the electric field and the K hat vector. Whereas the H plane in this case is the XZ plane. Okay, hopefully that makes sense. So E theta would be our desired polarization, right? Because E theta in the E plane is, the electric field is oriented along E theta um, when you look along bore side. The bore side is this along Z. Okay, so having said that, if we go back to our results and we can plot far, no, far field report, rectangular plot, polarization ratio. So we want spherical theta, right? Because that's the cross pole, co to cross pole ratio we want to look at, E theta over E phi. Okay, hit dB and then send your report. Oh, sorry. we need to plot as a function of frequency. And I'll set theta to 0 and phi to 90. The value of phi actually matters here. That determines what E theta and E phi are. But if you set it to 90, then E theta is equal to EY. Okay, and then E theta becomes the cross pole, the copole. Okay, so polarization ratio in dB is nice. It's very high. 10 gigahertz, it's around 50 dB or so. So what we can do is we can also plot the polarization ratio with E phi just to show you what it looks like. And that should be very low. Exactly the opposite, right? Because it's the inverse of this guy. So there's also this L3Y and L3X. So that is sort of the polarization ratio EY over EX. So EY component over EX component. This L3 business is what is called the Ludwig's third definition of polarization. You don't have to worry about it. That's kind of an advanced thing. But just for curiosity, you can also plot this. Let's do a new report. And we know that EY are polarization along at least the bore side direction, which is defined by these guys, is along Y hat, right? So that's why EY is very, polarization ratio with respect to Y is large. Again, in that direction, E theta and this definition and this definition are the same, only in bore side direction. Okay. Okay, I also maybe I can ask you a question. So what do you think will happen if I plot LHCP or RHCP? And so let's actually do that and see what happens. Okay, LHCP has some value. You can plot RHCP on the same plot. That's interesting, right? That they are almost equal. And they are equal to 0 dB. And the reason behind that is that linear polarization can be written as a superposition of LHCP and RHCP. So if you have very good linear polarization, that means you have equal components of both left-handed and right-handed circular polarization. So that's why the cross-pole, the core to cross-pole ratio, polarization ratio in terms of circular polarization is basically 0. And it's the same for both. But interestingly, at higher frequencies, we see that one polarization is dominating, right, which is the RHCP component. So there is in fact a second mode out here. And we'll see when we do patch antennas, maybe we'll see, maybe we won't. But that second mode, in fact, is more right-hand circularly polarized than left-hand circularly polarized. Okay. Maybe you can kind of also see that in the axial ratio, is that the axial ratio is dropping pretty fast, right? So it goes down to maybe close to 1 or 2 at higher frequencies because it's becoming more circularly polarized. Okay, so these are various quantities. The next important quantity that we want to look at is radiation pattern. That's probably the most important quantity. Okay, so typically radiation pattern is plotted in polar plot. So I can show you in both polar and rectangular plots. Sometimes it's also plotted in rectangular plots, so maybe it makes sense to do that as well. So we can say radiation pattern, which means it will plot it in polar plot. And again, we would usually plot the gain or the realized gain, or the directivity. All of them, you can plot either of them, but typically the gain is plotted. Okay, and here we don't want to plot at all frequencies, just at our basis frequency. Plotted as a function of theta, dB, and we only want the E and H plane, right? So we know that the E plane is the YZ plane, which means phi needs to be 90, and H plane is the XZ plane, which means phi needs to be 0. Right? So I'll select phi equal to 0 and 90. Control and select that. And then we can plot it. Okay, so the way it plots it, I actually don't like. So what I usually do is I add my own radiation box, infinite sphere, and I'll only set phi 0 and 90. Step size of 90. So minus 180 to 180 with a step size of 1. Okay, so it makes a new new far field setup. So I can go back into this and change my far field setup to this new setup, and then say apply. Okay, there we go. So now we see that we have our E-plane, which is this one, the green one, right? So in the E-plane, we have some lobes and some back radiation. And it's important to kind of understand where this back radiation comes from in the E-plane. And we'll see why that is. And in the H-plane, you have a nice smooth pattern, right? So these are two cuts of the full 3D radiation pattern, which you can also plot. You can say 3D polar plot, and then say gain dB. Here you should not use this one. You should use the full 3D, right? And then say new report. Okay, there we go. So you see that you have this weird two back lobes, right? So this is a 3D plot. If you want to see how this corresponds to the actual antenna location, you can go back here, say HFSS fields, plot field, radiation field, and we want to enable gain plot 2. And then we can scale this to 1. Apply, maybe that's too big. And I don't want to make it transparent. So we'll say transparency 0. Okay, so there we go. Right, so that's showing us exactly that in the E-plane, maybe I can add some transparency. Okay, so this is showing us that in the E-plane, which is this plane, there are these two lobes, right? And in the H-plane, which is this plane, those lobes don't show up, right? So really you have a 3D radiation pattern, but you're only plotting it in two cuts here. And that's usually good enough to represent what the beam pattern may look like, right? So, okay. It's also sometimes useful to plot the radiation pattern in rectangular plot. So let's do that. Far field report, rectangular plot, gain dB. And I only want it in my infinite sphere, and now I can leave it as all because you only have two, right? Say new report. And the reason behind that is that I want to know what the beam width is. Half power beam width, right? So again, I can put a marker. And of course, E and H plane should have the same value when theta is 0. Right? So you can add a maximum marker, which is 7.3269. And this should be in good agreement, exact agreement, in fact, with the gain that we plotted earlier. Right? At 10 gigahertz, the maximum gain was 7.3269. Once again, in bore side, so this is gain as a function of angle, that was gain as a function of frequency. Right? So here we're plotting at 10 gigahertz, taking the maximum. There we're looking at the maximum over frequency. Right? And they both should be equal because this is the total maximum. Actually, it's not the total maximum, right? It's slightly higher at a slightly higher frequency. But that's okay. But that's the peak gain. If you look at the realized gain, it's only high at 10 gigahertz. Okay, coming back to the pattern, we want to plot what's the radiation half power beam width, right? So we know that the maximum power is 7.3269. So I'll put another marker here, and I want to go 3 dB below that. Right, so I can go to 4.3269. Okay, and this is around minus 40 to 30. Let's say in H plane, it is around minus 40 to 40, which is 80 degrees. Whereas in E plane, it's a little bit smaller than that, around 75 degrees. Right? Another thing you can notice is that the H plane pattern is symmetric with theta. E plane pattern is not symmetric with theta. And the reason behind that is that the feed is not symmetric with theta, right? The feed is slightly offset. Whereas in H plane, it's completely symmetric, the entire structure. Okay, so that's about the half power beam width. So, okay, one thing I want to mention is you can actually use, let's say, the 80 degrees and the 75 degrees and the 4 pi over theta E theta H, which is the half power beamwidths in the two planes, and then take 10 log of that. And that will actually, so I actually just did that. I calculated it, and it turned out to be around 8 dB or so. Let me actually just quick check my calculation really quickly. Yeah, so around 8.3 dB should be the directivity from these values. And if you go back to our directivity plot, it's close to that. It's not exactly that. So I can put an X marker and then set this to 10 gigahertz, 7.8. So it's like maybe half a dB off. And that's not too bad for a very quick estimate of the directivity. Okay. All right. So this is the regular radiation pattern. You can also plot the normalized radiation pattern. So we can say new report. And that's the normalized value, dB10 normalized. Sometimes this is reported, sometimes the full radiation pattern with the gain included is also reported. So it depends on what you want to report. Okay, so we're done with gain, we're done with basically even directivity, realized gain, all of them give you the same pattern. The next most important thing to plot as a function of frequency is the Cohen cross-pole ratios. Okay, so I'll typically go to far field report. So for that, we'll use the electric field. So this is RE. So I want to use RE theta because we know that E theta is the copole. And then we'll use my infinite sphere. And I'll set phi equal to 90 degrees. So in the E plane, I'm plotting. So this is the E plane. This defines the E plane, right? Phi equal to 90 degrees. And we know in the E plane, E theta is the copole. Right? So I'll plot the TB value of that. That's the copole. And E phi is the cross pole. Add trace. There you go. So you can actually do this to check which one is max, which one is small, right? So E theta is very large, E phi is very small. Now, this is where it can get a little bit confusing. When I go to H plane, right? So I go to H plane. In H plane, E theta is the cross pole, whereas E phi is the copole. Let's plot it to see that that's the case. Right, there you go. E phi is large. Not magnitude, I want dB. So let's delete this. Okay, so we see that in the H plane, E phi now is the copole and E theta is the cross pole. And that really has to do with the fact that we are really converting between Cartesian and polar coordinates, right? So when you're cutting in this cut, at theta equal to 0, there is kind of a singularity, right? Because if you're coming along y-axis, if you're coming along this axis, then Ey becomes E theta, right? Whereas if you're cutting along the xz plane, Ey becomes E phi, right? So really the electric field is along Ey. And when you're looking at the yz plane, Ey becomes E theta, whereas in the xz plane, Ey becomes E phi. And along the z-axis, you have Ey, but that is neither E theta or E phi, right? It's the sort of a singular point over there. So the way HFSS kind of resolves that is that it sees, okay, you're plotting along the YZ plane. So it sets at theta equal to 0, it sets E theta as Ey. And along the XZ plane, it sets E phi equal to Ey. Right? So at that point, it's not really well defined. But hopefully, if you think about that a little bit, it makes sense that really the electric field is along EY, and in the E plane, in the YZ plane, EY becomes E theta, and in the XZ plane, EY becomes E phi. And you can kind of see that electric field is along this direction. So along the YZ plane, it's pointing along theta. Whereas if you move slightly to the right, if you're in this direction now, you have EY, then that is E phi, right? Because phi goes around like this. So that's why it gets a little bit confusing when you use this coordinate system. But that's okay. It's not that hard, right? So once you know this, that's why I always try to stick to one convention where I set my primary current for a linearly polarized antenna to be along Y direction. Then I know exactly what's going to happen. I know, oh, in the E plane, I have E plane as YZ plane, H plane as XZ plane. And then in the YZ plane, E theta is my copole, and in the XZ plane, E phi is my copole. Okay? All right. So these are your co and cross poles in the two cuts. All right. So that's usually pretty much all we care about when we're plotting different quantities, the beam widths, bandwidths, and so on and so forth. So the next thing we can probably look at is plotting the actual fields. Okay, so remove that plot. And what I want to plot is I want to plot the currents. Okay, so I'll hide this. I hit F to select face, and I'm selecting the ground plane face. Actually, before that, maybe we'll look at one more thing. We'll look at plotting the near fields. So I'll say insert near field setup, sphere. And now I can set a different, a specific radius, right? So let's say for this antenna, I'm look at, I just go to measure, say edge, and then I measure this edge, the E-plane edge. The E-plane edge is around 7.5 millimeters. And we know that the wavelength is around 3 centimeters, right? So now what we want to do is, okay, so what I want to do is I want to look at it at around, let's say 5 millimeters, right? So that's well in the near field. And once again, we'll just do 0, 90, 90, theta goes from minus 180 to 180, step size of 1 degree. Hit OK. And now we can plot the radiation pattern in the near field. So we have a new option now, create near field report, rectangular plot. So here we can only plot the electric and magnetic fields. So what I will do is I'm going to select E theta to TP. Families, we want to plot the E plane. Okay, so we look at the E plane, E theta component. What does that look like? So we see that there's a big discontinuity here. And the reason for that is that the near field is intersecting the ground plane. Right, so we can change that a little bit. So let's say I change this to 35 millimeters, so it's beyond the ground plane. And you can kind of see the points if you zoom out. And now we see that we have a nice smooth curve, right? Okay, we do want to compare this maybe with the far field in the E plane, right? So which was this one, copy data. Let's see if it lets me paste. Okay, did let me paste, wow. All right, so Rather than dB, I want to normalize this. So when you're normalizing the field, you need to use 20. Okay, let's make a new report. Normalize with 20, make a new report. And then say I want to put this into that. So I drag that into that. And now we can compare the near field and the far field, right? So you can see that the near field is the red plot, the far field is the green plot. And we are actually quite far away from the size of the patch, but still it looks something like this, right? So what if I make this 60 millimeters? Then you can see it's slowly converging to the actual value, right? If I make it 90 millimeters, and it's more and more accurate. Okay, so let's go back to 30 millimeters. Okay, this is sort of the edge. What you can also look at is you can also look at the phase, right? And that's kind of how far field is defined. So let's do that. So instead of this, I can say complex angle in degrees, Cang dig, right? And then say new report. And then that's for near field. Let's do the far field as well. Once again, I want to do Cang dig. This is what I want to look at. Sorry. This. Need to go back here and then say Cang degrees, new report. And I'll put this into this so we can compare the two. All right, so that's the comparison. Yeah. Okay, so maybe I can add a X marker. And then we want to see, okay, what's the maximum difference? So here it's like around 30 degrees or so, right? Maybe a bit more, maybe 35 degrees at most, or 40 degrees at most, right? So that's quite a bit more than what we expected, which is 22.5 degrees. And then I'll let you think about why that is when we're at 30 millimeters. If you're at 60 millimeters, then that phase error becomes smaller, right? So now the phase error is like 20 degrees, which is less than 22.5, right? So the answer is kind of, we'll see next actually, that the far field distance, which we calculate as 2d square over lambda, what should d be, right? So should d be the size of the patch, or should d be the size of the ground plane? That's usually something that people don't think about. But from here, we can clearly see that the far field distance is around 60 millimeters, right? So you can kind of set 60 millimeters equal to 2d square over lambda, solve for d, and d will turn out to be around 30 millimeters, okay? Right, because when 2d square over lambda is 30 millimeters as well. So if d is 60 millimeters, then 60 times 30 divided by 2 is 30 times 30. Square root of that is 30 millimeters. Right, so d turns out to be around 30 millimeters. And if we go back to our design and look at this, what is 30 millimeters here? Right, this size is only 7.5 millimeters. This is around 10 millimeters, whereas this is 30 millimeters and this is 30 millimeters. Right, so what we've shown here essentially is that far field seems to be corresponding to the size of the ground plane and not the size of the patch. And then we saw that when we set the far field to be based on the size of the ground plane, the error is less than 22.5 degrees, which is what we expect, right? And this R times E theta corresponds to the fact that essentially HFSS what is far field, right? Far field is defined at infinity, but at infinity, electric field should be 0, right? So it multiplies the electric field at a very large distance with the distance r. So it's sort of the normalized electric field at a very far distance, because we know electric field drops as 1 over r. So if you multiply with r, then you should get a value that's fixed and doesn't change as a function of distance, right? And that's what this r times e theta is. Okay, anyways, so what I've shown you here essentially is that the far field distance of the patch is determined by the ground plane of the patch, okay, and not by the size of this patch. And that actually nicely brings us to the next thing that we want to look at, which is so I hit F to select faces, which is the current. So I can plot field, plot J, magnitude of the surface current. Okay, you can plot that. That's what that looks like, but this doesn't really make much sense. So what we'll do is we'll go to scale and make it log scale. And then I go to use limits, and the maximum is around 300. So I can make the minimum 100 or so. It's too much. How about 50? Maybe the maximum was too high because of the lumped pole. Of course, it cannot be 0 dB. Let's use auto once again. And I'll limit the maximum to around 100. Just to visualize it a lot easier, makes it easier. Okay, so we see that there are actually currents going all the way till the edge, right? So you see that in this cut, because currents are flowing this way, there are currents going all the way till the edges. Right? So in fact, it is these currents that radiate. It's not the current under the patch. We'll see that maybe in the class that for a patch antenna, it's the ground plane currents that radiate. It's the fringing field that radiates and not the current under the patch. The current on the patch is kind of canceled by the current on the other side of the patch, which we can also plot. Select the top face, hit B to go to the bottom face. And we plot that. Plot field, mag J, okay. Okay, that's what that is. And we can also plot the top face. All right, so maybe we can look at one at a time. Block that. So block that. Okay, so the currents on the top face are basically close to 0. You don't have much current on the top face, right? And the reason behind that is that the excitation is on the bottom, right? So the mode inside the patch is generated between the patch and the ground plane, and very little current actually leaks from the sides onto the top. Okay. Whereas if I look at this current, so let me, it's invisible. Oh, HFSS crashed. Guess I made too many changes all of a sudden. So let me restart HFSS and come back to this point. Unfortunately, HFSS kept crashing again and again, but essentially the only last thing that I wanted to show you is that you can also animate the plot. So I'm sure if I click this, it'll crash again, but hopefully that doesn't happen to you. So if you click on animate and then hit OK, then you'll see that it will animate over one period what the fields look like as they are propagating. Sometimes that's useful, sometimes that's not very useful, but it's just an option that you can use. Okay, that's probably a good place to stop. So we discussed a wide variety of topics in HFSS today on what to plot and different quantities to plot. So hopefully this is somewhat useful to you, and hopefully it was interesting. And if you have any questions, you can leave them in the comments below. Let me know. If not, thank you so much. I'll see you in the next one.